Design of flat slab with direct design method (DDM). Conventionally, when slabs are supported on steel beams, then the design of slab is separated from design of beams and columns. However, if beams are absent or beams are flexible, it is not appropriate to separate the slab design. The concept of plane frame comprising column and slab beam member is taken into consideration. This is a slab beam member. This is the plan of a flat slab. This is slab beam member in east-west direction. This is slab beam member in north-south direction. Okay. When we make a longitudinal section over here, then we will get elevation something like this, and in that case, this is known as equivalent frame. Okay, this is an internal equivalent frame. Okay, if you take the exterior columns, then that will give you an exterior equivalent frame. Okay, flat slab is a two-way type of slab. Okay, flat slab is a reinforced concrete slab with or without drops. So if drop is present, then drop is considered as a part of slab. And column with or without column head. If column heads are present, then they are considered to be the part of column. Right? Okay. Slab panel is the part of slab bounded on each of its four sides by the column center lines. So these are the center lines of column. Okay. So in between area is known as slab panel, and this should have a two-way. Each panel is divided into column strip and middle strip as shown in uh, figure below. Okay. Okay. So this line is the center line of this slab panel. Okay. And this line is the center line of this slab panel. Okay. The in between distance is L2. Okay. So this is the width of the equivalent frame. So this slab beam member is divided into column strip and middle strip. Middle strip is a design strip which whose width is equal to 0.25 L2 but not greater than 0.25 L1, and this strip is on both sides of the center line of the column. Okay, this should be a 0.25 L2 or 0.25 L1, whichever is less. Similarly, this also. Okay, so this makes the column. Okay, now what is middle strip? So L2 minus width of the column strip divided by 2 will give the width of the half middle strip and half middle strip. So this is how the slab beam is distributed in column strip and two half middle strip. Now this is another slab beam member which is again subdivided into column strip and middle strip, and we will get an half middle strip over here from this slab panel, and this together will form a complete middle strip. Okay. So middle strip is always bonded with column strips on its two sides. Okay. So this is the column strip and this is another column strip. Okay. Now slab drop panel and column heads. So minimum dimension required for the drop. Okay. For an interior drop, okay, x1 should be greater than L11 by 6. This is L1. x2 should be greater than L1 by 6. This is L1. y1 should be greater than L2 by 6. This is L2. y2 should be greater than L21 by 6. This is L21. So x1 plus x2 gives you the width, y1 plus y2 gives you the depth. Okay, the dimension should not be less than x1 plus x2 and y1 plus y2. This is for interior drop. If it is an exterior drop, then x3 should be greater than x1 plus x2 divided by 2 plus half the width of the column. Similarly, y3 should be greater than y1 plus y2 divided by 2 plus half the width of the column. Okay, so these are the minimum dimension of required. Okay. Now this is a column head which is a part of column. Okay, this should make 45 degrees with the vertical. Okay, and so total angle should be 90 degrees. Okay. So this is the portion which is considered in design. Say suppose you are providing a larger degree than 45, uh, say suppose 60 degree, then the concrete below this line will be neglected, will not be considered in design. Okay? So only this portion will be considered in design. Effective depth of drop shall not exceed the thickness of slab. Okay, effective depth of drop will not exceed thickness of slab. This is thickness of slab plus x by 4. This is x. If there is a capital, and this is the distance. If there are no capital, then it will be from the face to the face of the column to the outer edge of the drop. Okay, that will be x. So effective depth of the drop shall not exceed the thickness of slab plus x by 4 plus effective. However, if the projection below the slab should not be less than one-fourth of the slab, this projection, right? This projection should not be less than one-fourth of the slab, and at least it should be 100. Okay. Following condition will be satisfied by a two-way slab system for application of direct design method. There must be at least three continuous span in each direction. One, two, three. One, two, three. Okay. Each slab panel should have a significant two-way slab action. This should be this should have a two-way slab action. Okay. The column must not be offset more than 10% of the span from either axis between the center lengths of the excessive column. The successive span length, center to center of supports in each direction must not differ more than one-third of the longer span. Say suppose this is your longer span, then this should not differ more than one-third of this longer span. Right? The factor live load must not exceed three times the factor dead load. This method is only applicable for gravity loads. This type of loading, the type of loading allowed is UDL. Live load and dead load are applied on all spans. Okay. The direct design method is a simplified procedure of determining the negative and positive design moment at critical sections in the slab beam member using empirical moment. This method is applicable for gravity loads only and not for lateral loading conditions. For the purpose of calculation of fluxus stiffness of slab beam member and column in case of DTM, they are considered to be prismatic. Okay, so you can use this formula, that is fluxus stiffness is equal to 4EML, and that means the stiffness of drop and column head if present are neglected. Okay. Total design moment of a span. Okay. Suppose we are having three span, then each span will have a total design moment, that is M0. Okay. So M0 is equal to W L2 ln square by 8, where W is the factor that total load, that is live load plus dead load in kilonewton per meter square. Ln is the clear span in the direction of MO measured face to face of column, capital bracket or wall, but not less than 0.65 L1. Okay. So Ln is the clear distance. Okay, clear span, right? If there are no capitals, then this. If there are capital or brackets, then Ln will be clear span between the capital or brackets like this. Okay. Now L1 is center to center length of span in the direction of the total moment M0. Okay. So this is the direction in which we are finding the total moment M0. Okay. So L1 is center to center between the columns. L2, length of span transverse to L1. Okay, transverse to L1. This is L1, so this is L2. Okay. This is L2. So L2 is the width of the equivalent frame. When the transverse span of the slab panel on either side of the center line of the support varies, okay, the L2 shall be taken as average of the transverse spans. Okay. Say over here, this is L2 and this is L3. If L2 and L3 are not same or equal, then you have to take average to find L2. Average of these two. Okay. Okay. Now, Code has given this formula. Okay. That is M0 is equal to W into Ln divided by 8, where W is the total load in kilometer. Okay. So W is equal to W into L2 into Ln, which you put over here, then you will get this. Now, at a joint, the depth and width of the column above the flat slab is taken as uh, BU and DU. Okay, and for a column below the flat slab, the width and depth of the column are taken as BB and DB. Okay, when drop panels are used, then the dead loads due to local thickening of the drop shall be taken in account for design. Now, longitudinal distribution of total moment M0. Once you find the total moment for a span, then you have to distribute it longitudinally. Okay. So first taking the exterior panel. This is exterior panel. This is interior panel. Okay. Interior negative design moment at C is given by this formula. This is given in the code. Okay. Exterior negative design moment at A is given by this formula. Okay. Positive design moment near midspan at B. Okay. So here, okay, this is given by this formula. Okay. So over here, alpha C. What is alpha C? Alpha C is sigma Kc divided by Ks. Okay, like Kc is the sum of the stiffness of the column meeting at the joint. Okay, so say suppose we are seeing joint number one, then the stiffness of column at top and bottom of the slab. Sum of that flux stiffness is sigma Kc. Right? And Ks is the flux stiffness of the slab falling at that joint. Now, coming to the interior span. Sorry. This is our interior span. Okay. Negative moment at supports D and F. D and F. Okay. So that has to be 65% of the total moment. Okay. And positive moment near the midspan E. Okay. That has to be 35% of the total design moment. Okay. So over here, right? So once you find once you distribute the total design moment longitudinally, okay, we have by this formula we have distributed our uh, total uh, total moment longitudinally. Okay, so the next step is apportioning of moments to column strip and middle strip. Then now we have to distribute these moments. Okay, okay. So for exterior panel, first we will see for the exterior panel. Okay, if the flat slab is supported on a column whose width is less than 0.75 L2, then whatever moment is coming over here will be 100% taken by the column strip, and the moment distributed to the middle strip will be 0. Okay. Now, the moment near the midspan is distributed transversely in proportion to 60% of that moment will be taken by the column strip and 40% by the middle strip, that is 20% by this half middle strip and 20% by this half middle strip. At interior support, okay, whatever the moment is coming longitudinally, that is distributed transversely. Uh, that moment will be transferred, so 75% will be transferred to the uh, column strip and another 12.5 and 12.5% to the half middle strips. Okay. So this is how it is transferred in case of exterior column. If it is an interior, yeah, sorry, exterior panel, if it is the interior panel, then at support, the negative moment will be transferred to column strip, that will be 75%, and 12.5 and 12.5% to the two half middle, and the positive moment near the midspan will be distributed, and 60% of that will be taken by the column strip, and 20% by this half strip, and 20% by this half middle strip. Okay. Now, if the support is a wall or a rigid beam, okay, when the width is greater than 0.75 L2, then the middle strip will also receive some negative moment. Okay. So whatever negative moment is at this section, then that moment, the part of the moment transferred to the column strip will be in this proportion: width of the column strip divided by L2 into mu, and the moment transferred to the two half middle strip will be in this proportion, that is zero point 0.5 into 1 minus width of the column strip divided by L2 into mu. Okay. Now, very important point is check for the effect of pattern loading. Okay. In direct design method, when the ratio of live load or imposed load to the dead load exceeds zero point 0.5, then you have to do the check for the pattern loading, right? If it is less than zero point 0.5, then it doesn't matter. So in that case, point A, F's alpha C is to be found. Alpha C is sigma Kc by sigma Ks. Sigma Kc is the sum of flexure stiffness of the column at the top and bottom of the flat slab, and sigma Ks is the sum of the flexure stiffness of the slab falling on the joint. Okay. So alpha C should be greater than alpha C minimum. Okay. Which is alpha C minimum is as specified in table 17 of IS 456-2000 page 56. So this is that. So this is a typical table. So let us understand that how do we find alpha C minimum. Suppose we take an example. Okay. Say the ratio of L2 by L1 is zero point 0.6. Okay, L2 by L1. Then it falls between these two values, right? Zero point 0.5 and zero point 0.8. So first we will interpolate and find alpha C minimum for this for the ratio of L2 by L1. When it is zero point 0.5, alpha C minimum is zero point 0.6. Okay. When L2 by L1 is zero point 0.8, alpha C minimum is zero point 0.7. Okay. Now we want to find for zero point 0.6, which turns out to be 0.633. So once you find this, now we will come to this imposed load by dead load. Say the imposed load by dead load ratio is 0.8, it falls between this values, right? So when it is 0.5, the alpha C is minimum. When it is 1, then alpha C minimum will be 0.633. So we get the second alpha C minimum, which is equal to 0.3798. So we have to take minimum of these two. Okay. Our alpha C should be greater than minimum of these two, which is this. Okay. So this is how we find alpha C minimum. Okay. Okay. Now, if alpha C is found to be less than alpha C minimum, then you have to find the factor, multiplication factor beta C, which has to be multiplied to the positive design moment of that span. Okay. So this is the formula given in the code, where this is the dead load in kilonewton per meter square, and this is live load in kilonewton per meter square. So now let us take a example. And the plan of two-way float slab is shown below. Okay. All the columns are 500 by of size 500 by 500 mm. Uh, all columns are of size 500 by 500 mm, both above and below the flat. Floor to floor height is 3.5 meters. Assumed live load is 5 kilonewton per meter square. Finished load is 1 kilonewton per meter square. Determine the design moment and the reinforcement required in the interior panel of equivalent frame in east-west direction using direct design method. Use M20 and A415. We will take the equivalent frame just over here, right? This is the interior equivalent frame. Okay. Now, First step is that do we satisfy the limitations of DDM first, or there are three continuous span in each direction. Okay, one, two, three. The panels are rectangular with long span to short span equal to 1.25, which is less than 2. So, okay. There are no offsets in columns. So, okay. There is no difference in successive span length. Okay. This is 6 meters, 6 meters, 6 meters, 7 meters, 7.5 meters, 7.5 meters, and 7.5 meters. So, okay, right. Only gravity loads are applied. Okay. And a type of loading applied is UDM. Okay. So we are satisfying all the limitations of DDM. Okay. Now, assuming the slab thickness. The thickness of flat slab should not be less than 125. L, we will take the greater of L1 and L2. L1 is 6 meters, okay, 6 meters. It is same for all the spans, okay, and L2 is 7.5 meters. Again, same for all the spans. Now, let us assume PT equal to 0.35%. So from figure 4, IS 456 2000, we take graph for FS 240 and get KT equal to 1.5. So this is the formula given in the code for L by D ratio. So L by D allowable is equal to L by D basic into KT into KC. For continuous slab, it is 26, KT is 1.5, KC is 1, so this is 39. Taking L2 as L, 7.5 meters, we get D equal to 192.5 mm. So let us take overall depth as 250 mm. Okay, and we are considering effective cover is equal to 50, so the effective depth of the slab is 200. Now let us assume the thickness of drop panel equal to thickness of slab plus 100 mm, because uh, projection below the projection of the drop below the slab should be at least 100 mm, which we just saw. Okay, so we are taking 100 mm. So the thickness of the drop panel is 350 mm. Again, in case of drop panel, we are taking cover effective cover as 50, so the effective depth will be 300. Okay. Now, dimension of equivalent slab beam frame, L1 is 6 meters, L2 is 7.5 meters. So first we will find the width of the column strip. Column strip is lesser of 0.25 L2 or 0.25 L1. So L1 is 6 meter, L2 is 7.5 meters. So definitely it will be 0.25 L1, that is equal to 0.25 into 6 is equal to 1.5 meters. So this is 1.5 meters plus 1.5 meters, so into 2 is equal to 3 meters. So the width of the column strip is 3 meters. Okay. Now width of the half meter strip is equal to L2 minus column strip. Okay. So whatever area we get divided by 2, that is 2.25 meters. This is 2.25 meters and this is also 2.25 meters, right? Now, size of interior drop panel. So from here, x1, okay, x1, sorry, x1, x1 is L11 is 6 meters. So 6 by 6 is 1 meter. X2, L1 is 6 meters. So 6 by 6 is 1 meter. Okay. Y1, Y1. Okay. So Y2 is 7.5 meters. So 7.5 divided by 6 is 1.25. Similarly, Y2 is also 1.25. So the dimension of the drop should be x1 plus x2, that is 1 plus 1, 2 meters. Y1 plus Y2, this is 1.25 plus 1.25, this is 2.5 meters. Okay. So this is the minimum dimension to be provided for the drop panel. Okay. But we will provide a drop panel equal to the column strip width and depth, width and length of the drop panel. We will provide it equal to the column strip, which is 3 meters. So size of the interior drop panel we are taking is 3 meter by 3 meter. Similarly, size for drop panel, exterior drop panel, this is 3 meters. Okay, okay, this is 3 meters, and this will be x3 is taken as 1.25. Sorry, x3 we are taking as 1.5. Okay, half of the drop panel. This is 1.5 plus the half width of the column, that is 0.25. That is 1.75. 1.75 into 3. Okay. Now, Ln is the clear distance between the column. Okay, so L1 minus 0.25 minus 0.25, that is 0.5, that is 5.5 meters. Now, let us first run this example through the program. Okay. Okay. Total number of span is 3 plus enter. All L1 for all the three span is 6 meters. 6 enter, 6 enter, 6 enter. Okay. So we know all the columns are width and depth are 500. Okay. Adjoint one. BU is width of column above the flat slab, and DU is the depth of a column above the flat slab, and BB is the width of column below the flat slab, and DB is the depth of the column below the flat slab. All dimensions are 500. Okay, so 500 press enter, 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 500 500, 500, 500. Okay. L2 is 7.5, F5 is 415, F6 is 20, height story is 3.5. Okay. We have taken depth of slab as 250. Okay. So we will take it as 250. Okay. So we will take it as 250. This we will take it as uh, okay. Uh, Depth of drop we have taken as 350. So 350. Okay. Length and width of drop you have taken is 3000. Okay. There are no capitals. Okay, 0. And the live load is 5. Working load. Okay. So we'll take 5. Finish. Write the dead load on the slab, excluding self bed. We have taken as 1. That is finish load. Okay. So this is how you can uh, do the design of the step. Okay. Now we will carry on with the program problem. Okay. Now, calculation of loads. Factor live load, that is 5 into 1.5 is equal to 7.5. Factor dead load, 1 is the finished load, 0.25 is the slab depth, and 1.5 is the factor, so we get 10.87. Additional factor dead load due to projection of drop, so 25 into projection of drop is depth of drop panel minus depth of slab, that is 0.35 minus 0.25 into 1.5, that is equal to 3.75 kilometer per meter square. So total factor load is 14.625, right? Now this is our total factor live load, this is our total factor dead load. So the ratio comes out to be 0.512. So it is greater than zero point 0.5. So the effect of load pattern has to be okay. Loading. Now the next step is to find the total design moment for all the spans. MO. Okay, as all the spans are same are of same length and the load acting on each span are same, so our total design moment for each span will be the same. Okay, so M0 is found to be 62 6 to 7.45 kilometer meter. Now we will distribute this moment longitudinally in exterior span. Okay, so first we will find alpha c. So we know first we'll find KC. Okay, KC, all columns are of size 500 by 500. So KC is found to be this much. KS is found to be this much. Okay. The formula and the values are written over here. Okay. L2, you have to take L2 over here. L2 is 7.5 meters. Okay. And D over here is you have to take as 250. Okay. So sigma Kc is equal to 2 into this value divided by Ks. We get 1.828. Okay. So for exterior panel, the total design moment when distributed longitudinally, the moment coming at the support C will be okay 430.029. Okay. The exterior negative design moment at A, okay, is found to be 263.62. Okay, and the positive design moment near the midspine B is found to be 281.73. Okay. Now next step is check for the loading pattern. Okay, because the ratio of imposed load to dead load is greater than 0.5, so we have to do the alpha c is equal to sigma kc by sigma ks, which is 0.914. So let us find alpha c from table 17 of IS 456 2000, as we can find the alpha c minimum as just I explained a few minutes ago from table number 17. The ratio of L2 by L1 is 1.25, corresponding alpha c is zero point 0.8. Okay. Similarly, find alpha c minimum for imposed load by dead load, which is equal to 0.512. Alpha c min is found to be 0.016. So we have to take alpha c minimum list of these two, that is 0.016. Our alpha c is this, which is greater than this. So as alpha c is greater than alpha c minimum, the column stiffness is adequate and modification for positive moment is not required. Okay. Now let us distribute this longitudinal moments transversely. Okay. So this is the table. Exterior negative distribution, exterior negative moment distributed to the design strip. Okay. The moment over here is at 263.62. Okay. And as the column, as the width of the column is less than 0.75 N2, so 100% of this moment will be taken by the column strip, and the moment taken by the half middle strips, this half middle strip and this half middle strip will be 0%. Okay. Now, positive moment near the midspan distributed to the design strip. Okay. So the moment over here we got is 281.73. So 60% of this moment will be taken by column strip and 20% by each half middle strip. Okay. So interior negative moment distributed to design strip over here, okay, is is found to be 430.029. So 75% of this will be taken by column strip and 12.5% will be taken by each half middle strip. Okay. So these are the moment distribution transversely. Uh, and once you know the moment, you can use this formula for finding EST. Okay. This is how the EST is found over here. But please remember, if this EST is found to be less than EST minimum, then you have to provide EST minimum. Okay. Okay. When the drop panel are provided, then the area of negative reinforcement calculated for this region, the additional thickness of drop panel measured below the main slab should not be greater than x by 4, 1 by 4 of x. So this is x in our case. This is, we know, 1.5. So 1.5 minus 0.25 divided by 4, okay, that is equal to 312.5. And this h we are providing as 100 mm. H should be less than x by 4. Okay, so 100 mm is less than this, so it is okay. Okay, we have considered effective depth of drop panel equal to 300 mm, and we have considered effective depth D for slab 200 mm. Okay, so this is found to be okay. Okay. Now distributing the longitudinal moment transversely in interior panel. Okay, so moment at support F is 407.84, and well, this is negative moment. This is positive moment near the midspan at E is equal to 219. Okay. Now we will do the check for loading pattern. Again, same steps. We found alpha C minimum as 0.016, alpha C is 0.916. As alpha C is greater than alpha C minimum, the column stiffness is adequate and modification of positive moment is not required. Okay. Now let us distribute this moment transversely to the design strip. Okay. Interior negative moment distribution of design strip. That interior moment is 407. Okay, and 75% of this will be taken by the column strip, and 12.5%, okay, will be taken by the other half bit, two half bit strips. Okay. Positive moment near end span distributed to design strip. That moment is 219.6, and 60% of this moment will be transferred to the column strip, and other 20 and 20 to the half middle strip each. Okay, and coming to the interior negative distributed interior negative moment distributed to the design strip, that is 407.84. That is over here. Okay, that is over here, right? Okay, so 75% to the column strip and 12.5% to half middle strip. Okay. So this is how the moments are distributed, and EST is found by this formula. Okay. If this EST is found to be less than EST minimum, then you have to at least provide EST minimum. This is what we just saw about. So we have considered effective depth of drop panel is equal to 300. We have considered effective depth D for slab is 200. Okay. This remains the same as well. Okay. Now, these are our longitudinal moments. Okay. So we can see at this common joint, the moment over here is 430.029. The moment over here is 407.84. So there is an unbalanced moment of 22.189 kilonewton meter, which will be taken by the column. Okay. So this moment has to be transferred to the column. Now, as we know that the width of the equivalent frame is much larger than the width of the column, so this total moment will not be transferred to the column by flexure. Part of this moment will be transferred by flexure and other by torsion, right? So we can see in this figure, this strip, that is C2 plus 1.5 D is effective depth. This is C2, okay? This strip will transfer part of the moment to the column flexure by this action, okay, by this action, right? Now, the other remaining unbalanced moment will be transferred by these two imaginary torsion member through torsion. Okay. This you can see there's a torsion over here, imaginary torsion member, and produce shear over here, right? So this torsion will produce shear, and the remaining moment will be transferred to the column through shear. Okay, and here we have to add to the actual punching shear stress, right? We will see that. Okay. The unbalanced moment at the interior span is transferred to the column by flexure and torsion. The area of the slab within uh, the area of the slab with width equal to width of column plus zero point 0.5 effective depth of the slab transfers the partial unbalanced moment to the column by flexure. That is, the remaining unbalanced moment is transferred to column by torsion through by torsion member to torsion. So these are the torsion members. Okay, so they will transfer remaining moment to column with as shear. Okay, this torsion will produce shear at the face over here, as I showed over here. This will produce shear over here. And so this is how this unbalanced moment is transferred completely to the column. Now, as per clause 31.4.5.2 IS 456/2000, and an interior support, the supporting member above and below shall be designed to resist the moment M given by the following equation. Okay, so we will have to find the moment using this equation. So this moment, the column over here at top and bottom has to be at least designed for this moment. Okay, so if this moment is found to be greater than this, then we have to consider. Okay, WD is the dead weight, WL is a live load. Okay, in kilonewton per meter square. Okay, WD dash is the dead load for the shortest span. Okay, but our span are same. Okay, so our in our case L1 will be equal to Ln dash, L2 will be equal to L2 dash, and WD will be equal to WD dash because the spans are same. No span is long or short. Okay, so putting all this formula, alpha C, we have found that 0.914, we get moment equal to 32.5, which is greater than 22.189. Okay, so we will have to consider this. Okay, now we will have to uh, uh, transfer this moment to the column as according to the stiffness, closure, and right. Transfer as flexure. Okay, interior support. We are taking interior support. So first we will have to find lambda using this formula. Okay, C1 is the depth of the column long span, C2 is the width of column transfer to the span. In our case, C1 is equal to C2 is equal to 500. So lambda is found to be 0.6. So moment transferred by flexure is zero point 0.6 into unbalanced moment. We are taking this as a moment that is equal to 19.5 kilonewton meter. So this strip will transfer a moment of 19.5 kilonewton meter to the column flexure, right? Now, moment transfer by torsion. So the remaining moment is equal to unbalanced moment minus the moment transferred by flexure. Unbalanced moment we are taking is 32.5 minus 19.5, that is equal to 13 kilonewton meter, which is transferred to the column through shear, and this shear has to be added to the punching shear stress. The effective depth of the D of the drop panel is 300. Okay, so this is a part. Okay, this is the torsion, imaginary torsion member, which will transfer the torsional moment to the column. Okay, so for finding the additional shear stress, this is the formula: moment divided by polar moment of inertia into A by 2. Okay, what is A? A is over here. This is column, this is D by 2. Okay, so A is equal to 800, B is equal to 800. This is the formula for finding J, polar moment, for interior column. So J is found to be 0.106. Okay, putting all this value over here, we get additional shear stress to be added to the punching shear stress at this section equal to 0.049 Newton per meter square. Okay. So we will add this additional shear stress when we do the check for punching shear stress. Okay. Now, for exterior span, okay, edge beams are provided on the periphery to take the torsion coming on the exterior edge. In the exterior span, the exterior negative moment is 263.62. Okay. This moment is uniformly distributed throughout the spandrel or edge beam for a length of L2 equal to 7.5 meters. Or L2 is 7.5 meters. So this is distributed over this length, right? This spandrel beam are designed for torsion bending moment due to load coming on it and shear. These edge beams are preferred to have the width at least 300 mm or more, as it has to resist large torsion moments. Owing to the presence of the edge beam, the large part of torsion is transmitted to the column in form of shear by the beam action. However, for simplifying our calculation in this problem, in this example, we are neglecting the contribution of beam action, and which will lead us to a conservative solution. So we are neglecting the effect of edge beam load. That is, we are only considering the slab over here for transferring this torsion as shear, okay, which will give us a conservative solution. But for ease of calculation, for this problem, for this example, we are doing so. Okay. Okay. Now, our this is our moment into point 4, that is 105.44. This is the moment that will be transferred to torsion to the column. Okay. So J for the exterior column is found by this formula, which is 0.0734 meter raised to 4. Now again, using the same formula, A is found to be A is equal to this much, okay? C1 plus D by 2, and B is equal to C2 plus D, okay? Right? So putting these values, we get additional shear stress as 0.465 Newton per mm square. So this will be added to the punching shear stress at this section. Okay. So let's proceed. Now we will do the check for one-way shear for interior span. Actually, you have to do for exterior span and interior span, but over here we are just doing for interior span. Okay. So total factor load is 22.125 kilonewton per meter square. So we will check at two sections. One is at a distance d from column, and another is at a distance d from the rod. Okay. So check for one-way shear at section 1, that is at a distance d from the face of the column. Okay. We know this is 6 meter. Okay. So this is 3 meters. Okay. So we will see. We will take it at a distance d. Our section at a distance d. Okay. So we are taking 1 meter strip over here. So length into width into W will give the total shear force that has to be resisted by this section over here, right? So Bu1 is equal to total load into 3 meters. This is 3 meters minus D into 1. Okay, that is 59.74. So tau V is found to be 0.199. PT we found to be 149, okay, percentage from our above design, which we found the steel, okay, for interior panel. From table 19, IS 456-2000, design shear strength for concrete uh, for this PT is found to be 0.28, which is greater than tau V. So it is one shear at section 1 bar. Okay. Now check for one-way shear at section 2. So we will check from the face of the drop. Okay. So this is 1.5 meters plus D. Okay. This is 3 meters, right? W into 3 meters minus 1.5 plus D into 1 meter, that is equal to 28.76. Okay. So again, tau we found as 0.144, tau C is again 0.28, tau C is greater than tau V, so it is safe in normal shear, right? Now coming to the check for punching shear stress, right? Again, over here, we will take two sections, okay? First, we are taking the interior panel, okay? Interior panel. One at a distance d by 2 from column, and another at a distance d by 2 from the okay, at a distance d by 2 from column, okay, this section falls in the drop. So the depth, effective depth is 300. So first we have to find the peripheral length. So this is going to be 500 plus d, that is 300. So this is 800, 800. So 800 into 4, that is 3200. Now Bu is equal to the load acting on this area minus this area. That will give the area uh, outside this periphery, right? Okay, so this area is this minus this area into load will give us the total VU, that is 981.465 kilonewton. So tau V is equal to VU by BO. This is BO into effective depth is 300. That is found to be 1.022. Now we have to add the additional shear stress which we got due to torsion, okay, transfer of torsion to shear stress. That was found to be 0.049. So we have to add this, which is 1.071. The permissible punching shear stress is found to be 1.1, which is greater than this, so it is safer, okay, in this section, right, over here. Now, at a distance d by 2 from drop panel, okay. So our drop is 3000 by 3000 plus this section falls in slab, okay. So the effective depth of slab is 200. So 3200, 3200, 3200, 3200. So total periphery is found to be 12800. Again, VU we find uh, by this area minus this area. We get the area outside this periphery, right? Into W, okay, that is equal to 769.065. So tau we find is found as zero point 0.3, which is less than permissible 1.1. So this is okay. Now coming to the check for punching stress and a single column. Okay, a distance d by 2 from column. Okay, 500 by 500 is a column, and over here this falls in the drop panel. So the effective depth D is 300, D by 2 is 150. Okay. This is 500 plus 150, this is 500 plus 300, and this is 500 by 150. So D is equal to 300, periphery is equal to 2100. Again, VU, this area minus this area into W gives VU 527.78. Tau V is found to be 0.837. Okay. Again, adding the additional shear stress which we got for the exterior column as 0.465. So total tau V total is 1.3. Permissible is 1.11. Okay. 1.1 is less than maximum tau C, so it's okay. But it is also less than tau V. We will have to provide shear reinforcement. Okay. So this is the formula for finding the area of shear reinforcement legs, area of legs required. Okay, so that turns out to be TV total is 1.3, 0.5 tau C, zero point 0.5 of this. Okay, BO is known to us, 20. D is known to us, that right? So we get area of steel ESV required is 1300 mm square. Okay. Now we want to find the number of legs. Then ESV divided by the area of stirrup bar into the number of sides. So number of sides that we have to provide shear reinforcements are 3, 1, 2, and 3. Okay. So as we are providing 8 mm dia bars, so area of stirrup bar is 50.28. Number of sides 3. This gives 8.6. Number of legs we will provide 10 legs. Okay, so 8 dia stirrups, 10 leg stirrups will be provided at a distance 0.75 d, say 200 to center space. Provide these stirrups up to a distance. Provide these stirrups up to a distance from the column to a point where shear stress does not exceed 0.05 tau. So we will provide the stirrups in whole drop panel. Okay? Right. Now at distance d by 2 from drop panel. Okay? So we are taking the section at distance d by 2 from the drop panel. So this is going to be 1725 plus 100 because this section comes in a slab. Okay, so the effective depth now will be our 200. Okay, so the periphery is found to be 6850. Okay, VU is this area minus this area into W 410. Okay, tau V is 0.3, permissible shear stress is 1.1, so it is safe. Okay. So this is how the all the calculations for a flat slab has to be done. Now comes the detailing part, right? This is summary. Reinforcement detailing for equivalent slab beam spanning in east-west direction. Exterior, exterior span, exterior support. Exterior span near mid support, mid span. Exterior span, interior support. Interior span, interior support. Interior span near mid span. Interior span near interior support. So first we will draw the reinforcement detailing for a longitudinal section through the column. So we will take this steel first, right? Okay. So this is the longitudinal section. So this turns out to be 12 mm at 125 mm. Okay. This turns out to be 12 mm at 125 mm. Now over here, okay, over here, and the area of steel required over here and area of steel required over here are different, but we will take maximum. Okay, we will design this joint for the maximum steel. So we will take that is 12 mm at about 100 mm. Okay, coming over here, we will take 10 mm at 120 mm. Coming over here, we will again take this steel. We will take again the same. Okay, maximum of the that is 12 mm at 100 mm. So and inside the drop provide a minimum reinforcement mesh, 12 mm about 3 mm center to center. Okay, all the lengths required uh, to be satisfied are written over here. Okay, and this over here we have to provide shear reinforcement, that is 8 dia, 10 leg steers about 200 mm center to center. So this is going to be like this, and you have to provide it on the with spacing where 200 mm from the column face. Okay, 200, 200, 200. Now, similarly, and now below is the reinforcement detailing for a longitudinal section through the middle strip. Over here, we will provide twisting. Okay, so that is provided over here. You can see this mindfully, and you can try to understand that how the detailing of a platform can be done. Hope you